Mental overview of spin polarization signature. So let me start with a brief introduction. So this is a cartoon of heavy ion collision. So as you know that there are two important feature, especially in non-central collision. One magnetic field, and another one is the orbital angular momentum. So a strong magnetic field will be created due to the spectator proton fast moving along the beam direction. So the magnitude would be the 10 to 13 Tesla based on the rough estimate. So if we compare to the, for example, typical magnet or even the magnetar, which is a strong magnetic field of the neutron star in the universe, still our magnetic field is much higher than those value. And for the orbital angular momentum, it's about 10 to 6 h bar, which is also very fast. And these two features lead to the so-called chiral phenomena and the spin polarization. And so those magnetic field and also the angular momentum point to the perpendicular to the reaction plane. So both contribute to the global polarization. So in case of the angular momentum, due to spin orbit coupling, a particle and the antiparticle spin are aligned in the same direction. While in case of the magnetic coupling, a particle and the antiparticle spins are oppositely aligned due to the different opposite sign of the magnetic moment. But again, the both contribute to the global polarization. And experimentally, one can measure the polarization of the particle by using the weak decay of the hyperon, where the parity is not conserved, meaning that your daughter particle or baryon is highly correlated with the parent spin direction. So this is this formula is based on distribution of the daughter baryon in the parent rest frame. Here the P is a polarization and alpha is a decay parameter. So in case of the lambda, so lambda decay into the proton and pion is roughly 0.73. Actually, this value has been recently updated because of new result from base 3 and the class. So originally it was a 0.64, but now it's become 0.73. So yeah, roughly 40% difference. But the old plot shown in this talk are based on the old alpha value. Sorry for that, but yeah, at least for star we are trying to update our old plot. So then how to measure global polarization? So again, the global meaning the specific direction. I mean the spin alignment along the, especially for the initial angular momentum direction or magnetic field direction. So basically we need to project polarization to this angular momentum direction, which is again perpendicular to the reaction plane or impact parameter direction. So experimentally, we can determine the azimuthal angle of impact parameter direction by measuring this spectator deflection. Then our polarization definition can be written as follows. So here is a mean sign, psi1 minus phi star p. Again, this phi star p is the azimuthal angle of the daughter proton in the lambda rest frame. And this is a resolution of the event plane angle. So this is our definition. So just to show you how to measure the polarization. So this is a star event TPC event display. So first we need to identify the pion and proton daughter of the lambda. So by using the TPCD DX information or time of flight information, then we can make the invariant mass Then applying some cut on the decay topology, one can clearly see the clear peak of lambda. And the bottom panel, so the y-axis is a kind of the low polarization. This means sign component as a function of the invariant mass. You can see that clear signal around lambda mass region, which is opposite for lambda and anti-lambda because of the different signs of the decay parameter for lambda and anti-lambda. Eventually, both contribute to the positive polarization. And experimentally, the major lambda, most of the major lambda are coming from the field round, such as a sigma star or sigma zero or psi. So if your parent particle R is also polarized, that polarization also will be transferred to the dot lambda. So here the SR star is your parent particle spin vector, and this is your dot lambda spin vector, and C is a polarization transfer factor. So this C depends on your decay process. So it could be positive or negative. So since we have a field down effect, we have to consider this effect. So based on detailed study in this paper, so the effect is found to be roughly 50 to 20%. So the primary lambda polarization will be diluted, but this value also model dependent. Also, this relation tells us that the polarization dot particle or dot lambda can be used to measure your parent polarization, for example, the psi or omega. So I'll come to the point maybe in the end of this talk. So first paper of this global polarization has been appear in 2007 from star experiment. So this left panel as a function of durability for two different collision energy. So as you can see that the data point are basically fluctuating around zero. So conclusion at that time is basically the result were consistent with zero, giving just upper limit, which is 2%. And then 10 years later, star again looked at the low energy collision data. Then we observed positive polarization, as many of you know. So the polarization signal seemed to increase in lower collision energy. So based on the local thermal model of the local thermal equilibration, so the polarization can be decomposed to two components. One is the vorticity term and also the magnetic field, contribution from the magnetic field. So by taking the average the lambda and the anti-lambda polarization, one can roughly estimate or calculate the vorticity omega, assuming certain temperature. And it was found that roughly 10 to 20 seconds per second. So it is the most vertical fluid that has been observed. And also this red symbol is for anti-lambda, which seems to be slightly larger than lambda. So this might be a hint of the effect from the magnetic field. And yeah, I will discuss it later a little bit more. Then Star also revisit the 200 ZB data by using the high statistics data taken recently. And this most light data point is a new result for 200 B with roughly 5 sigma significance. And this new result also confirms the energy dependence of the polarization. So at 200 ZB, the polarization signal is roughly 0.3%. And here you can see several lines, the model calculation from viscous hydro or NPT calculation. And also there are a lot of other calculations, the chirokinetic approach or other type of the hydro calculation. So basically, all of them can reasonably describe the data very well. But in my understanding that most of the calculation, they basically calculate the local vorticity at the freezer, then convert it the polarization. And also there are new results and also Hades experiment. So here again, the collision dependence, energy dependence of the polarization, the most right data from the Alice experiment for 2.7 and 5 TeV direct collision. So they are currently consistent with their the current statistical uncertainty is almost similar of the expected signal. But maybe hopefully the next run 3, they can improve the this significance statistical error. And if you look at the Hades experiment preliminary result, this orange symbol, this is for 2.4 ZeV in gold-gold collision. It seems that this data follows or are very close to zero, but this has a large uncertainty. And based on the theoretical expectation, both the kinematic vorticity and the thermal vorticity predicts that the vorticity will drop off around the 2 or 3 ZeV. So in that sense, this data seems close to that expectation. But of course, this has a large uncertainty that should be improved. And for this, especially at the lowest collision energy, in addition to the star-fixed target mode and also the best 2 data can probe this energy, especially for 3 to 7.7 B. And we are working on that, but most of the data actually already taken. And as I mentioned, you saw the slight difference between the lambda and anti-lambda polarization, although the difference is not significant in terms of statistical error. But on this formula, one can also calculate this magnetic field at the result like this. Again, the error bar are consistent with zero, but some positive mean value. If you calculate the average of this value, it roughly becomes the order of the 10 to 13 Tesla, which is large actually. But yeah, having better precision of the data, we may be able to constrain the lifetime of the magnetic field, which is unknown and also depends on the conductivity of the quantum plasma. But yeah, of course, there could be other effect to make this lambda and anti-lambda splitting. I listed here, but yeah, you may know the other effect. So yeah, sorry if I missed something, but yeah, there could be the effect of the initial magnetic field. And in addition to that, there might be the effect of chemical potential, which is expected to be small. But also recently, this paper shows that the rotating charged fluid also produces the magnetic field with longer lifetime, which also creates the anti-lambda splitting, although the uncertainty is also large. And for this paper, the spin interaction with meson field also can be generated by the baryon current, and that also lead to this lambda and anti-lambda polarization splitting. And lambda and anti-lambda might be emitted at a different time or a different space point that also lead to the splitting. So there are a lot of many effects, so we need a caution for the interpretation. And then moving to the differential measurement of the polarization. So first, this is the centrality dependence of the polarization. So as you naively expect that in most central collision, there should be no initial angular momentum. Therefore, the polarization decrease in more central collision that is seen in this 200 dB data. And recently, there are preliminary results for lower collision energy, 54 GB and 27 GB. We also see such a trend of the central dependence for both energy. And we also look at PT dependence for 200 GB. So naive expectation is that we may have this polarization due to, for example, scattering at the low PT and also the effect of the fragmentation at the high PT. But the data 200 dB does not show any clear PT dependence. Of course, the error bar is still large, but also the hydro model predicts similar weak PT dependence. The different initial condition may lead to slight difference. And if you also look at the 54 GB and 27 GB, we also didn't see any significant PT dependence. Another thing is that miscellaneous angle dependence. So polarization measured in plane and also the out of plane. So the data shows that the larger polarization in plane direction than in out of plane direction. While many of the model predicts the opposite trend, that is a larger polarization in out of plane compared to the in plane, like this. So I think this is not fully understood yet, and there might be some update from the theory talk. But yeah, this is one of the puzzle. And we also look at asymmetry dependence. So idea here is that if we have this strong magnetic field, then there might be the chiral separation effect, meaning that the actual current will be induced along the magnetic field with non-zero vector chemical potential. And if we can kind of the probe or select this event by event fluctuation of the vector chemical potential, then of course the actual current means that there is a spin polarization effect. So that if we can select this current or vector chemical potential, then we may have the additional contribution to the polarization from this effect. And the left plot shows the polarization as a function of charge asymmetry. Here, a charge is basically the number of charged particles. I mean, the positive particle minus negative particle divided by sum of them. Assuming that this a charge is proportional to the vector chemical potential. And here, red data point for lambda and blue is for anti-lambda. There seems to be a charge dependence in the polarization, and that slope seems to be opposite for lambda and anti-lambda. So this might be a possible contribution from the actual current, but in this talk, so the chirokinetic approach, they also show that the clock vector chemical potential may explain the data. And I showed the global polarization result, but also there is a result or study on the global spin alignment using the vector meson. So in case of the vector meson, which is not the weak decay, so parity is not conserved. So we cannot directly determine the direction of the polarization, but we can structure the spin density matrix rho 0, 0. So in the similar way that your daughter particle can be written in this way. So here, 0 is a diagonal element of the spin density matrix. And since the vector meson has a spin 1, so the possibility is that plus minus 1 and 0, so there should be state. And if the particle is not polarized, those states should be equally taken. But if there is some polarization or alignment, there should be the deviation from the 1/3. So the deviation from the 1/3 in the rho 0, 0 indicates a spin alignment. that deviation may depend on the hadronization process of the quark or the source of the spin alignment. I guess in the next talk, they will discuss in detail. But in the data, actually, Alice and the star measure this rho 00. So the left two panels show the rho 00 as a function of the number of participants or centrality, let's say. For K star and phi meson, so red symbol is for low PT and blue symbol for high PT. So for low PT, we clearly see the larger deviation from 1/3. And if you look at the right two panel, which is for static result, again the K star and phi meson for 200 ZeV, and this is for both 54 and 200 ZeV. There's no significant energy dependence. So considering the vorticity picture or polarization of the lambda hyperon, the deviation from this from 1/3 of this rho 00 is too large. So this cannot be explained by the vorticity picture because of that vorticity is a second order effect in the rho 00. And also another puzzling is that K star and meson at leak is opposite trend. They are both deviating from the 1/3, but in the opposite direction. Or you could say, if you compare to the phi meson at the leak and LHC, that is also opposite. And recently, there's a theoretical paper say that the mean field of the phi meson may explain this data. But yeah, maybe in the following talk, maybe they will clarify that such model can explain the whole picture, including phi meson and K star and both and LHC result. Moving to the local vorticity. So far, we are discussing about the global vorticity or polarization effect. Of course, if you look at the part of the system, there should be the local vorticity which would be different in the phase space. So the left plot shows just examples of the energy density profile in the transverse plane, where this arrow shows the flow velocity, where the jet pass through from left to right. Then clearly see along the jet axis, you will see this vortex ring here. And similarly, such local vorticity will be induced by collective flow. For example, at forward and backward rapidity, because of the longitudinal expansion, there might be this kind of the vertical effect. And one can naively expect that such local vorticity also can be created by the elliptic flow, since we know that there's a stronger expansion in plane compared to the outer plane, which naively lead to this kind of local vorticity, which along the beam direction, and its sign depends on the azimuthal angle. And similar to the polarization, a global polarization, we can also measure it. Basically, we need to project the polarization vector to the beam direction. So here, this longitude polarization is basically proportional to this cosine theta star p. And the star experiment measure this longitudinal polarization. So this y-axis is kind of signal of this PZ as a function of the azimuthal angle relative to the second order event plane. So as you can see that this data show this sign structure, which is consistent with the expectation from the elliptic flow. But as we know that many models actually cannot describe this sign, but some of them can do. But yeah, please note that the most of or all model can reasonably describe the global polarization, but not this polarization. And here I listed several work by our colleague. And for example, the hydro MPT calculation shows the opposite sign in the sign phase, while the chirokinetic approach or this PICR hydro model predicts the same sign as the data. And there are more detailed study in this paper that there are several contributions to that longitudinal polarization, and there are some competing effects. And depending on the relation among these contribution or components, there might be it could be a positive or negative. But many of models are the local thermal equilibrium, while, for example, chirokinetic approach doesn't assume. So it might be related to the incomplete thermal equilibrium of the spin degree of freedom, because longitudinal polarization, if it's coming from the elliptic flow, it probably developed at the later time compared to the global polarization, which coming from the initial angular momentum. And this is a longitudinal polarization that a sign modulation of the longitudinal polarization as a function PT. So data that show a clear PT dependence. There might be a hint of the of at a low PT region, but uncertainties are a little bit large. And again, the hydro calculation predicts the opposite sign. And here there are two bands. This is from the Brastway model calculation. That is a hydro-based simple model. So basically, here we calculate the vorticity using the Fourier-out parameter, which I extracted from the fit spectra and V2 and HBT, then convert it to the polarization using this formula. So this is a formula used in displacement model calculation. So interestingly, this simple model can describe the data well, and the inclusion of the HBT results also slightly affect. And if you look at the centrality dependence, first of all, the data also increase in more peripheral collision. And that Brastway model also captures the trend of the data. And again, that inclusion of the HBT will not somehow affect the magnitude at the peripheral collision. So this is a experimental outlook. So since I'm the STAR member, I don't know about so much about the other experiment, but for STAR, we took the statistic data for in the beam energy scan 2 program, which covers 7.7 to 19.6 GB. Also, we had data with a fixed target mode, which covers 3 to 7.7 GB. And we also had the isobar correlation data, which is expected to have the 10% difference in the initial magnetic field. So it might be interesting to look at especially lambda and anti-lambda splitting. And also we are working on the global polarization for multi-strangeness particle like Xi or omega. There is an interesting prediction from in this paper that there might be the spin or mass order of these particles in the polarization. And also STAR is planning to have a forward upgrade, especially in the SX era, which is around 23. So the right bottom panel shows the projection plot. So this is a polarization as a function of rapidity. This is for 200 GB. So currently, we don't see any clear rapidity dependence, but some of the models predict opposite direction, especially at for rapidity, either growing or drop off. And have ITPC also the we will have the forward tracker around this region. We can measure the polarization covering this range. And this red data point is a projection for lambda. So error bar would be this at the forward rapidity, it become larger. And also we can measure xi and omega polarization with this precision. And for ARIS or MS and Atlas, I think some of my friends are working on global and local polarization at 5 TeV, and that all will be done in round 3, the high statistical data. And for hardest, I'm hoping to finalize the 2.4 GB result with some improvement on the statistical, not statistical, systematic uncertainty. And of course, it would be interesting to look at the lower collision energy at the future experiment, like a FAIR or NICA or JPAC. So towards Xi and omega polarization, I just want to discuss a little bit more. So especially for Xi and omega, it becomes very difficult because of smaller decay parameter. For lambda, it's about 0.7, but for Xi, it's 0.4, and omega it's 0.01. So it's almost impossible for omega. I mean, the direct image as omega polarization. But probably one can use the daughter lambda polarization to know your parent polarization. So this is a formula for based on the Lian. So this is for the daughter lambda polarization in decay of Xi. So eventually your daughter lambda polarization can be written with this simple formula. Here C Xi lambda is a polarization transfer. So in this case, roughly 0.9. And similarly, for the omega case, the polarization of the polarization of the delta lambda from O can be written with this formula. But the problem here is that this gamma omega is not known. I mean, it's not experimentally measured. But considering this time reversal violation parameter beta is small, and also considering this relation among alpha, beta, gamma, so this gamma omega would be probably close to +1 or -1, which leads to this polarization transfer either +1 or -0.6. So this is also interest. So based assuming this Bautista picture, we can also determine the uncertainty in this gamma omega or this polarization transfer. But then several questions arise. Of course, first, what about the polarization for different spin or magnetic moment, especially for these 3 particles? And this lambda from Xi, decaying from Xi, should have defined polarization. And maybe true if the Xi is produced at a different time. And of course, for this polarization transfer of omega. And experimentally, the polarization of Xi or daughter lambda will be measured in different frame, either in the rest frame of Xi or lambda. So are they defined or same? Also, I just want to mention that measuring Xi and omega are very challenging in terms of the statistics. So compared to number of lambda, so the for Xi, it's roughly 10%, and maybe in case omega, it's almost 1% at 200 dB. And actually, I'm personally working on this measurement, and because of some collaboration reason, I cannot show the new result today, but actually the paper draft is currently under the collaboration review. So we are hoping that that new paper will be submitted in 1 or 2 months. So you will see new results soon. So this is a summary. So the global polarization of the lambda has been observed in gold-gold collision at 7.7 to 200 ZeV. And we find that the most Botica fluid is created in heavy ion collision. And we observe the energy dependence. So polarization increase in the lower energy. And those results are very, very described by theoretical model. So far, we don't see any significant difference between lambda and anti-lambda polarization. And there's a puzzle on the azimuthal angle dependence, which is not fully understood yet. Regarding the global spin alignment, which shows the larger deviation from 1/3, which cannot be simply explained by this vorticity picture or based on the lambda polarization result. And phi meson field may explain this large deviation, but there's some still question that model can explain whole picture, I mean the result from Lick and LC and defined particle, phi and k. And also the star experiment observed the polarization along the beam direction at 200 ZeV. So results are qualitatively consistent with the picture of elliptic flow. But yeah, as I discussed, there are several, I mean that there is a disagreement and also agreement among the data and many other theoretical calculation its sign. So yeah, there are many open questions, and yeah, as an experimentalist, yeah, we are working to get a more precise data. Yeah, actually that's all, and maybe it's a little bit too early.
Okay, thank you very much for your interesting overview and the update of the data. We have, in fact, a lot of time, so please ask questions. So if you want to ask a question, click on the raise hand button. So, okay, Chemin Ko, please go ahead with your question. Unmute your mic, because otherwise we don't hear you.
Yes, I have two questions. One is experimental questions. Can you show the rapidity, the dependent lambda, your planned experiment on rapidity? Dependent, yes.
Yeah.
What puzzles me is, if I remember the polarization, global polarization at 200 GeV is tiny. Why the data shows such a larger one, almost 0.2%? Oh, that's right, small, that's right. I'm sorry, I didn't know the scale correct. Yeah. So now that's no indication. Why don't you measure the rapid dependence at the lower energy instead of a 200 GeV? The rapid is large, polarization larger, the signal will be cleaner, right?
Yeah, we are working on that. And yeah, I think that probably I forgot to include, but there is a preliminary result for 54 GeV and 27 ZeV. And we didn't see any significant rapidity dependence, even at the lower energy, within our acceptance.
Okay, there's another question from Chun Wang. So,
yes. Also, yeah, you show the curve of the geometric model, right? Then you know, our paper published in last year on the physics review research. Also, we predicted with a hydro 3+1 dihydro. Also, this is the curve is similar to the geometric model.
I see.
Yeah. So this is actually this paper I show you is on page 17. Also, my another question is about. Please go to 17, page 17. Page 17. Right, 17. Okay, there. Then you see this. I just mentioned that paper. This is by Hong Zhongwu on the physics review research. On that paper, we predicted that the rapidity behavior is similar to the geometric model. It's also increased with the rapidity. This is a, yeah, my next question is about this figure. Then you show that the pH as a function of phi with respect to the reaction plane. Actually, in our paper on the physical review research, we also predicted this, that the behavior is the same, but the magnitude is different. Actually, it's much different. It's a little bit smaller than the data. The trend is we reproduce this trend correctly by if we assume we use the temperature vorticity, then we can get the right trend, but not the magnitude. Our magnitude is smaller than the data. That's the one of my comment. Thank you.
Okay, thank you. So let's.
Yeah, so your average global polarization is also on the.
Yeah. Our average polarization is just this, roughly.
Okay, roughly.
Okay, let's switch to the next question by Francesco Beccatini. Francesco, go ahead. Francesco, you have to unmute your mic.
Can you hear me?
Yes, now yes.
Okay. So I have a let me first. So I have a question, but let me first make a comment to the last question. Then so if you then Chung said that you can say reproduce the behavior, but you have to change the vorticity. Namely, that instead of the thermal, you have to change the
temperature.
Yeah, of course, that is one of the mysteries. I mean, it is unexplained why it is unexplained why the T vorticity works and the thermal vorticity, which is say which has solid theoretical foundations, doesn't. I mean, maybe it is a problem of not achieving local thermal equilibrium.
Yeah. This is part. I think this is one reason, but
I think this will be discussed over this workshop.
Okay.
However, maybe I have a specific question to Takafumi. Is the questions about his questions that he listed in the, I think, one of the last slides concerning the P star of sigma and psi, something like, oh, sorry, lambda xi. So it's one of the questions. Yeah, this one. Yes. So what do you mean here by P? First, P psi star and daughter P lambda star are measured in different frames. Are they different? What do you mean by this?
Yeah, so experimentally, so to measure psi polarization, we basically look at the lambda distribution in psi rest frame, right?
Right. Okay.
To measure this daughter lambda polarization, we basically measure the granddaughter proton distribution in the lambda rest frame.
Right.
So yeah, that's what I mean with different frame.
Oh, okay. But the relation which is written to the Lee-Yang formula, which is written in this slide, those vectors, the P lambda star and P psi star, they are measured in the respective rest frames. Namely, the P star lambda is the polarization in the lambda rest frame, and P star psi is the polarization vector in the psi star frame.
Oh, okay.
So, and the same is the formula that we quoted in the paper with. So the P star with the coefficient P star implies that these vectors are measured in the respective rest frames.
So at least in
I think
the frame is one.
No,
okay,
what I mean is the P psi star is the polarization vector in the psi rest frame, and P lambda star is the polarization in the lambda rest frame.
Okay.
So they are measured in different frames.
Right. I see.
And then I have a question. So about your second question, should lambda from Xi have different polarization? What do you mean by this? If Xi
yeah, this is maybe unclear indeed. Yeah, what I mean is that well, maybe yeah, this is indeed unclear, and even I can't remember what I wanted to say. So
okay. Okay, well, are there any further questions? I don't see so. If you, oh, there are some new questions. Shu Guang, go ahead.
Yes, I have two small questions. First one is that are you going to measure spin alignment for other vector mesons like row meson or other? I mean, in addition to the phi and the k star.
And k star. At this moment, I don't see any analysis that is trying to measure row or other particle inside the star.
Okay. Okay.
Yeah, at this moment.
Okay. Another small question is that. Yeah, is that I noticed that at the 200 GeV, the lambda polarization, global polarization, is slightly larger than the anti-lambda global polarization. Although it's not significant, but from the numbers, slightly larger.
Right.
Well, at the lower energy, we know the anti-lambda polarization is larger.
Yeah.
Yeah, is there any comment or?
Yeah, we noticed that, of course, and yeah, we don't have any clear explanation, but what we can say that this is what we get from the data. But yeah, if you look at the error bar, this difference is also not significant. So yeah, yes, we don't claim there's a difference, even we don't say lambda is larger than anti-lambda at this moment.
Okay. A final question is, oh, sorry, can I?
Oh, go ahead, we have only one.
Oh, yes, okay. The final question is that when you use the blast view model to describe the local polarization, you can describe the data. Well, when you use the hydro model, you cannot. Yeah, but blast view is the simpler hydro. So what I mean, why blast wheel can but hydro cannot describe the local polarization? Or what how to say, what is the essential difference in your blast wheel model and those hydrodynamic calculations?
Yeah, a similar question I received during star collaboration and the other conference, and
okay.
Yeah, I don't have the clear answer to that. Maybe actually I want to ask same question to other theory colleague actually.
Okay.
Yeah.
Okay.
Sorry. Yeah, I don't have answer to your question now.
Oh, okay. Thank you. We can discuss during this workshop.
So there is another question from Umut. I'm not sure about the pronunciation of your first name.
Yeah, that's perfectly right. Well, hello everybody. I'm Umut Gürsoy. Thanks very much for the very nice talk. I have a question about the magnetic fields that, you can, from the difference of lambda and lambda bar polarizations, you may be able to also extract the magnitude of the magnetic field. And my question is how much in detail, I mean, what are the error bars you can put on the magnetic fields?
So first of all, we first need to make sure or measure if indeed we see any difference between lambda and anti-lambda experimentally. And that can be done in the beam energy scan program. So the analysis is ongoing, and probably in a few years you will see the result. Then next question would be, is it really the effect of the magnetic field or the other effect like listed here? And so maybe it's not the answer to your question, but this is what I can say for now.
Yeah.
And the magnetic field is based on this picture or model, that is the magnetic field at the result. So in some sense, in the model, within this model, we can constrain the lifetime of the magnetic field.
Right. Yeah. So here in these formulas, you're already assuming, I think, that the magnetic field is small at the freeze out. Right? Is that compared to omega? Yeah. Okay. I see. Okay. Well, if I have time, I may ask another question.
Yes, we have still something like 7 minutes, I guess. So go ahead.
Okay. Yeah. Well, I was absent, unfortunately, in the first slides of your talk. I was at a different meeting. So maybe you discussed this already. So I was wondering, how sure can you be on? Well, it's a very general question about the polarization is coming from the spin orbit coupling and vorticity. This is the general belief that we all have. How certain can we be on this? I mean, there may be some other kind of transport effects that we are kind of ignoring because hydrodynamic model is not complete and all that. Are there any other checks that one can perform on vorticity? I mean, for example, when you quote a number on vorticity, 10 to something, 30, is the largest number. This is this should come with error bars, right? So that and can we be really certain on the error bars here? If we are not really taking into account all the effects, all possible effects in hydrodynamics, including non-equilibrium effects and all that?
Yeah, again, assuming the model written here.
Yeah.
So.
Yeah, I see. Okay.
And I don't put any experimental error bar for this estimate. This is just for kind of rough idea or rough discussion, but
Okay, so let's turn to still two questions. Yuri Karpienko, please. Thanks. Go ahead, Yuri. Unmute yourself.
Hey, do you hear me?
Yes.
Okay, so I was thinking a bit, I mean, mainly last few minutes about this question about the lambda polarization being described in the blast wave model and in real hydrodynamics. So I mean that's indeed interesting question. What's the difference? Like why one gets the longitudinal dependence and the other doesn't? So well, in principle, what we found with Francesco when we first found the reason for the structure in the hydrodynamics is that in the hydrodynamics you can express that the overall polarization signal via the gradients of temperature at the freeze out or via acceleration. Now this is all completely absent in the blast wave. So in the blast wave you basically have gradients, space gradients of flow velocity. So maybe that's what makes things different, that there is basically no time gradient of flow velocity. But I need to double check actually before my tomorrow talk. So that was another comment.
Okay, so another question from Masoud. Please go ahead.
Hi. I wanted to make a comment about the magnetic field here. And the comment is that this magnetic field that comes at this constraint on the magnetic field is very small, actually. If you compare it with pions mass squared, yeah. So, but the thing is that if that constraint is true and you want to put a constraint on the initial magnetic field, it is actually better for for us, I mean, for people that are interested in the effects of magnetic field, that the magnetic field, I mean, decreases fastly, because you can have a larger magnetic field at the initial times than it is predicted by the ideal emission limit or things like that. And if magnetic field is not large enough, it is very difficult to assume the classical treatment of a magnetic field. I mean, the very meaning of magnetic field is almost broken if it is that small. That was my comment.
Okay, so I guess this was a comment. So I think we have still 2 minutes. So Francesco, you wanted to give another comment, I guess.
Yeah, this is a general comment. I think that many questions that have been raised are very interesting, and since they deserve more time, I think that maybe we can. I want to remind everybody that there is a roundtable discussion at the end of the session today. So, for instance, the questions about whether thermal vorticity or the questions raised by Umut about, is there any other say possible signal of vorticity and so on and so forth. I think that we will have more time at the end of the
day.
Of the session. Yes.